Right?
Good morning. It's a pleasure to have Professor Babak Haghigat from YMSC Chingor, who will tell us about Liouville CFTs, matrix models, and constrained WZW. Thanks.
Yes, thank you. Yeah, so it's a pleasure to be here and give a talk. So, yeah, the original title was a little bit different, but it's going to be the same topic. So you can view the original title as a subtitle. And but I thought it is more suitable to roll up everything from a slightly different perspective. So let me start with the motivation for the talk. So basically, the motivation is twofold. So first of all, we will be interested in what is known in the physics community as a 2D, 4D correspondence. And here, so this comes from, this is basically motivated from six-dimensional superconformal field theories, and you can compactify them on the one hand on Riemann surfaces, and on the other hand on S4. And on the 4D side, you will get, n equal to 2 superconformal field theories. And on the 2D side, you will get the 2D Liouville CFT. And the conformal blocks of Liouville CFT are done on that particular Riemann surface are then equivalent to that of the Nekrasov partition function of the 4D gauge theory. And what we will be in this talk, what we will be mostly interested in are so-called irregular operators here. So we will have irregular operators, and I will come to explain what those are. And these are connected on this side to 4D Argyres-Douglas theories. So these are theories which don't have a Lagrangian description, so it's harder to deal with them from the point of view of localization and so on. But then this side gives actually many insights to these theories. Another perspective which I want to emphasize here is, which is also part of the motivation. So one motivation is to understand here these Argyres-Douglas theories and so on. Another motivation are topological phases of matter. And mathematically, these are described by TQFTs, so topological quantum field theories. And we'll be interested in, for example, if you have certain defects in your system and you want to braid them, or anyons and you want to braid them, that is basically governed by a topological field theory and what is known as the KZ equation. So we will be deriving KZ equations for these particular theories where you have an irregular defect. And also, this is also important for 3D gravity, because recently it has been shown that 3D gravity, or quantum gravity actually, is related to Liouville theory. And I mean, this has been known for a long time, but recently there has been a lot of progress there. And these irregular operators might be interesting from that perspective as well. So what I mean here is you have a 2D surface, and you have here some sort of irregular defect, if this is, let's say, your adiabatic time direction, and you can have other operators, so-called degenerate operators, and they can perform braiding when you go in time. And we'll be interested to compute how, let's say, if this is described by a wave function, how this braiding then acts on this wave function and what representations you will get. So these are the main motivations. So let me now come to the actual story. And I'll be starting with the second topic, namely matrix models, because it turns out to be easier to basically define all the things we need in Liouville theory starting from matrix models. Okay. So now consider basically the following matrix model, namely the action is given by some, this is the partition function, it depends on n integrals, and so it's an integral over an n by n unitary matrix, and there will be a potential. So it is defined as the path integral over these matrices, e to the minus trace of a potential of these matrices, and this is basically the main object which we want to compute. And here this measure, d phi, is given by 1 over volume of this un, and you have also the product from k is equal to 1 to n of d phi kk over 2 pi, and product of k less than j of 2 times real part of phi kj and d of the imaginary part of phi kj. So this will be the measure we'll be interested in, and also the volume can be written here. This piece can be written as product from k is equal to 1 to n of 2 pi to the k over k factorial. And the potential up there, which we use here, this potential is a sum from n equal to 1 to infinity or to any order of Tn phi to the n. So this is the unitary, basically. And so this is the setup, and then we can put everything now together to arrive at the corresponding measure here. So this is actually a very formal development, and I will come exactly to that situation. So this will have certain consequences, and I will actually assume formally that these are formal variables which are non-zero, and we'll see what happens. Exactly. I will take it. Physically, later on, I will focus only on models which have a finite degree here. I will never look at infinite degree. Yeah. So now we put everything together. So we basically get the following expression. So you have now this result, which is dwi e to the minus vwi, and here you have I less than j, wi minus wj squared. So let me call this one equation 2 and this one equation 3. And this piece here basically comes from this measure which we are using. So these are exactly these UN matrices, so it will contribute to this type of measure. And these are the eigenvalues of this matrix phi, which is inside this potential. Okay? Yes. No. This can be complex in general. In the complex, so this will be a locus if you want. Yeah. Okay, so in that sense, it will be, yeah, maybe it's called the Hermitian case. Hermitian, yeah. Okay, yeah. Right. Yeah, so the Lie algebra, but later on, we'll be interested in paths which are not only along the real line. Yeah. Okay, so yeah. Well, you can take it as the GL or whatever. Yeah. So okay, so this is basically, I want to actually start with this to come to the main story of Liouville theory. So first of all, let's look at operator expectation values. And here we can actually compute objects in this way. So this is n dwi o e to the minus b and I less than j wi minus wj squared. So this will be such an expectation value up to some normalization factors. And finally, I'll be interested in looking at translation invariance of the following expectation value. So we will have the following identity, namely del wi plus 2 times j not equal to I, 1 over wi minus wj plus ntn w to the n minus 1 times z minus wi, and you have n. So I'm taking as operator basically this 1 over z minus wi and sum over them, and then look at the total derivative should vanish, and then I'll obtain this equation. But this equation actually has many equations because it gives you an infinite number of constraints which should all vanish. So infinite number of constraints on the original function Zn of v. So what are these? So it gives me an infinite number of constraints, and these are basically all written in as follows. So you can write them now as z minus z prime, t z prime, and n t. And you will find that this t has to take the following form. So I'm now jumping a little bit, but it should be clear in a moment. So you can define this field of eigenvalues as tn z to the n plus trace of log z minus phi. So if you do this and take the derivative square and plug it in here and perform this this integral here, where the contour runs over around all the eigenvalues except for the z here, then you will see that this is basically equal to this, and you can expand this condition here, or alternatively that condition in powers of z, negative powers of z, and then each power will give you an infinite number of constraints which come from the modes here. So we will have, okay, maybe before I come to that, I will rewrite this one also as this piece plus n log z plus z to the minus n del tn, where I've used the definition here. So we can use this equation 2 to actually replace, we can expand in powers, so where yeah. Okay, trace of phi to the n here is replaced by del tn. This is basically using this particular ansatz for the potential, you can write it in this way. Okay. And once you then perform, so this is actually equivalent to that, and you can expand in powers of z, which I'm going to write here. So expanding in powers of z, get the following constraints. So we have now ln z n t is 0 for n greater or equal to -1. And these ln's here are just the Virasoro generators, but now expressed in terms of these derivatives with respect to t. So you have del tk, del tn minus k, plus k is equal to 0 to infinity, k tk del tn plus k. So what we find is that, so what you do is you can expand here in powers of z, and you perform these integrals, these contour integrals, and you pick exactly these constraints here. And this is nothing else than rewriting the original translation invariance of that original matrix model. Okay? So you'll see that you get these modes. Now the interesting thing about these modes is that they actually satisfy the Virasoro algebra. I will come to that in a moment. But I'll be more interested in these derivatives appearing here, because they will give rise to a Kac-Moody algebra in this case. So what we find is that we have these modes, which are alpha minus n equal to n tn, and alpha n is equal to derivatives with respect to tn, and here n is taking, say, greater than 0. If you define these modes in this way, they will satisfy a Heisenberg algebra and which will give us basically a U1 Kac-Moody algebra in the quantized case, and then you can rewrite this. You can basically recognize this expression as the corresponding Virasoro generator using the Sugawara construction, using these generators here. Okay, so this is what I wanted to show, starting from these integrals involving this formally infinite matrix, formally infinite potential here, but the symmetries will basically give you these generators here, and we will obtain, of course, this particular realization of the Virasoro algebra with central charge here, of course, equal to 1. So this will be changing as soon as I'm going to deform the model in the following. So any questions so far? Yeah. Yes? About what?
I understand that you integrate over the unitary group of matrices n by n.
Yes, that's what I thought, but then you said it's, this is something I have to check. I thought that because I'm usually not working on these matrix models, but I thought this is a good way to start it. Yeah. But you say it's the Hermitian one. Otherwise, you won't get this. Yeah. So we integrate over the Lie algebra, but that's what I'm saying. This is usually the radial part of the measure, because now I want to deform away. You mean to the power? The power is different? No, this is along these are non-compact lines in the complex plane. They are not just phase, they're not compact circles. complexified emission maybe matrix model. But I'm going to deform now to the to the case of SON and SPN, where the 2 is replaced by 1/2 or whatever. So yes. Okay, then that's basically the story. So yeah, any other questions so far? Okay, so then let me actually come to the formation of the story. So now I want to do the generalization to Liouville theory. So you see that, in fact, what we want this this object here, which this T here, to have not this particular form, but we want it to have this form. So Tz should be del phi square plus q del square phi, where this q here, say, is this kind of thing. And of course, this beta you can set, if you want to really connect to Liouville theory, you can set it to minus 1 over b squared, and you get this usual b plus 1 over b. But how do we get there? So you have to actually consider, so these things, these constraints, which we have here, so these will give you these constraints. These are known as loop equations. And in the following, we want to modify them. So we consider the so-called modified loop equations. And these go as follows. So you take here now the same matrix models, but slightly changed. So we have still the integral over all these eigenvalues. And we have 1 over z minus wi. And here we have now not to the power 2, but 2 beta. And we're going to introduce this potential, sum over L v WL. And this delta here is the product from, over this Wi minus Wj in this way. But now it's taken to this deformed power 2 beta. So this beta is equal to 1/2. 1 and 2 gives you the corresponding generators, the measure for these generators of SU or UN or SO or SP, respectively. But more generally, you can just continue for complex beta, and I mean you can define a model in this particular way, and this should be understood as the same potential there. You can, if you want, you can absorb these things into the T's. But if I don't absorb them into the T's, I will call the coefficients x. So if I look at these equations here, where I'm using now translation invariance of this new matrix model, of this new measure, so let's call this equation 6, then I can again do the same story. So I can again re-express that equation as such a contour integration over some t expectation value of some field here. But now the field is a little bit different, and the t is also different. So it turns out, if you go through the algebra, it's actually very easy. You will find that you will now get the following. So let me write it down here. Okay, so what we find is that we have to define this phi slightly in a different way. So we do 1 over square root of beta and n greater or equal to 0 to Tn z to the n plus square root of beta times trace of log z minus phi. And then we can use all the equations we have. So we have here, let me call this one equation 5, and we can now use equation 5 here, and 6 gives us the following, namely the ln's, the constraints. So it can be, again, you basically now have to use this t, and you can actually rewrite these constraints again in this way. But now the ln's will be a little bit different. So what you get is this one. So let me write it down. You get beta and sum from k is equal to 0 to n del tk minus n and k and tk here and minus square root of beta q n plus 1 del tn. So I will obtain this particular generator. Yes, there was a question? Temperature.
If I look at that, that integral that you have there, it's very natural to think of the Haghigat transition, where delta is the van der Waals determinant.
Right, that's a van der Waals, yeah. That could be, yeah, that could be. I see. So, but you want to look at the different phases in this case. Yes, you have of course this duality here as well. So this beta going to or square root of beta going to 1 over square root of beta. That is the duality. Maybe it will it is equivalent to that. So this system exhibits that duality. Indeed, yeah. But I want to rewrite this again in terms of these alphas. So what I find is that these becomes alpha k alpha n minus k minus q n plus 1 alpha n. So I will get now this particular algebra, and it will satisfy the Virasoro algebra. So they satisfy the Virasoro algebra with the following central charge, namely C is now 1 plus 6q squared. So before, this beta was 1, and the corresponding q was 0. So because as you see, it is just 0, so you will get C is equal to 1, but now you can in fact get this one, and it is known that this is of course the same as the central charge in Liouville theory. And in fact, it gives you a free field realization of Liouville theory, which is something we can, we can actually write down next. So, any questions about this deformation? Okay. Okay, so let's come to the free field realization. So now we have the beta deformed matrix model. We have now as coefficients, I call them x, and the definition is as before. So you have this delta to beta e to the VWL, and maybe here sum over L. And this VW is just xk over k, w to the k. Now, this thing here can be actually rewritten as dnw is equal to 1 to n v 1 over b wi e to the contour integral around infinity vw del phi, and acting as on the vacuum. So now this is a free field realization where this v here, v say alpha of some z, is just the normal ordered operator given in terms of this field phi, and then you perform basically all the corresponding Wick contractions, and you will see that you get exactly this result. Okay, so you have, these are basically screening charges here, and so that and the vacuum here actually satisfies the charge n condition, whereas so that you get charge neutrality. And you see that you can actually recover the matrix model by doing all the free field contractions in this case. So this is the free field realization of this particular thing. But what is it computing in the case of Liouville theory? So this is now the question: what is this? What kind of correlator is this in Liouville theory? So that's the important or interesting question. Yes? Mm-hmm. Yeah. Yeah. Exactly. That I don't know. It's just that as an integral over these eigenvalues, it looks like that. And for particular values of beta, you know, beta is a 1/2 or 2 or so, you get these different groups, but it's kind of an analytic continuation. So that I'm not sure what it means, but it won't be very relevant here. But yeah, it would be interesting to look into. I'm not sure if anyone knows. I mean, but I'm. Right. I'm just taking the result there and deform the result of the integral over the eigenvalues, right? So I'm just deforming the expression in that sense. But maybe this is something we can discuss later, because I wanted to come to a particular point here. So let me now define the following state. So this state I for irregular is defined as the integral here of this VW del phi acting on the vacuum, where now this V is taken to be a finite degree polynomial. So this is basically here given in this way, or you can say take TK if you want, so that we don't worry about what factors here. If you define such a state, this is a so-called irregular state. So that means that now if I take my generators alpha here, which are given in terms of derivatives with respect to these t's, then you can in fact write them as follows. So okay, I did write the potential in terms of these x's. So you see here, this is a little bit different. So you can either write it in terms of the t's or the x's here. So it's just t would be xk divided by k times the square root of beta over gs. If you take now these x variables, which are equivalent, then you can express all these alphas in terms of x. So that's what I want to do. So what you find is that alpha 0 acting on this will give you some eigenvalue lambda. You can take alpha minus I acting on it. It will give you I del xi acting on this irregular state, where now I is between 1 and r. Moreover, you can also take this one, again for I running between 1 and r. And the rest will act in a more natural way. So the other oscillators will actually act as n del xn, and for n greater than r. And alpha minus n acts as xn I, also for n greater than r. So you see, these actions are more familiar, because if you have, of course, these negative oscillators, they will generate for you the module. So if the module is a polynomial ring of these x's, it will just generate it in this way. Whereas these guys will actually get rid of x's. So if this is just a constant, they will usually kill the vacuum. These are highest weight representations. Usually in a highest weight representation, the eigenvalue is lambda, and then every positive mode will just kill it. But here it's different, because these positive modes, their role is switched for the modes between I and R, as you can see. So these are irregular states, and so these are irregular representations of the Kac-Moody algebra generated by these alphas, but it's also an irregular state of the Virasoro algebra using the Sugawara construction there. So, well, for the basically the Q-deformed one. And you will find that you also get irregular states there. So let me just briefly write an example. So for r is equal to 1, you will get that L0 acting on this is just lambda q minus lambda plus x1 del x1 acting on this. And L1 is x1 q minus lambda acting on it, and L2 is minus x1 square over 4 acting. So you see, these positive modes of the Virasoro algebra don't kill it. I have just assumed here that the rank here is, or the degree of the potential is just 1 to make things simple. But in the simple case, you see that L0 acts in a kind of non-diagonal way, and these guys don't annihilate the module. So these are irregular Virasoro modules as well, and irregular Kac-Moody modules. And okay, how are we doing? Okay, good. So any questions so far about the construction of these irregular states? Because now what I'm going to do is reinterpret this object here as a particular Liouville conformal block with the insertion of such an irregular operator. So, the x used to be that's why I rewrote this again. These are the coefficients of this potential, and they generate for you this new vacuum, if you want, and then everything acts in this particular way on it. Okay. So now you have, and R gives you the degree of irregularity, if you want. So, right. Okay, so far so good. So we have these sets of Virasoro generators, but what is this matrix model computing? So let me write it down. Okay. So we have this irregular operator. We can also have a so-called degenerate operators. And these are just V minus K over B, 2B, say. So this B, maybe you shouldn't be too confused about this. One can sometimes call this beta to be minus 1 over B squared to connect to the usual B parameter of Liouville theory. And this is just minus K over B phi Z. And this K here is an integer. This isn't the generate operator because it will create a null state at a certain descendant degree. And then you can compute in Liouville theory objects or correlators or conformal blocks of this form. So you have this V minus Ka over 2B at positions ZA times this irregular operator at infinity. And this is now in Liouville theory with central charge given by this 1 plus 6q squared. And you can see that the path integral will localize exactly on these types of matrix models and these which admit these particular free field realizations there with further insertions of operators, which are now these guys here, these degenerate operators. So this is basically the object which we are computing. And if we have, of course, I didn't discuss this operator in the matrix model. In the matrix model, this just corresponds to the following. So you'll be having an overall function of these z's, which is trivial. But then you're going to have, you can rewrite this in the matrix model as follows, where these O's now, O, let's call it Ka, OKA is now ZA minus product 1 to n Wi to the power of Ka over B. So if you include these operators in the matrix model with n by n matrices and this particular potential given by these x's, then this is exactly computed by this expectation value of this operator. Okay. So now this is of course all good, but we actually don't know Liouville theory in this way. Liouville theory can be constructed more naturally in as a constrained WZW model, which I want to come to, because this third viewpoint will be actually important if we want to look at braiding of these operators, because this was one of the motivations at the beginning. We want to start from such a conformal block and then braid the operators around each other. And for that, we will need the KZ equation, and that usually is derived in the context of WZW models. So now the next thing will be to, in the remaining time, to check how we can actually derive these things from the point of view of WZW theory. Okay, so before I come to that, any questions here about the definitions? Okay, so the third topic here is Liouville as constrained WZW. And so now consider the following action as WZW of G, which is minus K will be now some level. So this should be 8. And now we will be integrating over some boundary. And so this B3 is a manifold, a 3-manifold at this boundary, and the action is defined in this way. Okay. Now, for what we can do is, so this is the usual WZW action. Now, for G in SL to R, we have the following decomposition. So you can write G as ABC, at least close to the identity, where A is 1, A0, 1. This B is e to the phi 0, 0, e to the minus phi. And, well, there is also some C here, which is actually 1B0, 1 in this particular way. Okay, so it admits this kind of decomposition. And now you plug it in. You plug it back in to this particular action. Okay. So what you find is that SG is actually S of A, B, C. And then you can simplify a bit. And what you obtain is the following. Plus del minus A, del plus B, times e to the minus 2 phi. Now this is all classically, not in the quantum case, but you see, this looks a bit similar to Liouville, but still different. But if you look at the classical equations of motion, you will have the following particular solutions. So particular solutions of these equations of motions will be e to the 2 phi. The derivative of B is this. The derivative of A is this. And you will have that phi itself satisfies this equation of motion. So you see now, this is basically the Liouville equation of motion of the Liouville field. With these, and you basically have to constrain your WZW model. So this is all classical, but you will have to impose these constraints at the quantum level, and you will have the Liouville action. Now, since we can realize Liouville theory in this WZW theory, we can actually look at KZ equations in this WZW theory and see how it actually, how they look like when we constrain to Liouville theory. So we will have the KZ equation. So there is the thing we want to start is the so-called operator KZ equation. So this one is for a operator G here. It's given in this way. Acting on G, where these are actually the currents. They should be understood as operators acting on this, but I want to keep things classical at the moment. So then we will make the following ansatz. So if you make the ansatz E is equal to beta and H is equal to minus 2 gamma beta plus kappa alpha, and F is equal to minus 4 gamma square beta plus 4 kappa alpha gamma minus 2 kappa gamma prime, and you define A, which will turn out to be the same A as there, to be just minus 2 gamma. So these beta, gamma, and alpha are just fields. They will have, of course, this beta and gamma will turn out to be the beta-gamma system. But for now, these are just some classical fields. If you plug it in there and solve this equation, you find that you will obtain a nice solution which is compatible with what we had before. So now I'm going to use the same decomposition for G and plug it in here. Okay, so G is equal to A, B, C. And what you obtain is the solution now looks as follows. And so on. Okay. So this is the solution. And now we just compare to these constraints here. And this way we can actually solve for these beta and gamma fields. So comparing with star gives then the following solution. So beta is mu, gamma is minus nu over 2 integral z e to the 2 phi dw, and alpha is just our original alpha, which is namely just the derivative of this phi field. So now we have solved all these things. You can compute energy momentum tensor, and you will find that even that matches nicely. So you can actually compute the energy momentum tensor as 1 over in the WZW model with these constraints. So it's usually given by these Casimirs, right? And what you find is that this is just kappa del phi squared minus 2 gamma prime z beta plus kappa q the square phi, plus actually one more field, mu nu e to the 2 phi. So this is what you find, and you can, okay, sorry, this is just like this, okay? So this is basically the Liouville energy momentum tensor. These guys will just contribute to negative modes of the Virasoro algebra. So that's why they didn't appear in the loop equations. But this piece we recognize as appearing in the loop equations. And what you can now do is you can actually write down using this construction. This was for just one operator, but you can now extend it to the case which I was interested in the beginning. Namely, I wanted to compute the story of, I wanted to actually do the braiding of these degenerate operators in the presence of this irregular operator. So we have now all the tools in place, and we can actually use this to derive a more general KZ equation for that case. And I'm just going to write this down, and then should be finished. So from this, we can actually deduce the general KZ equation. And for simplicity, I will again restrict to irregularity rank is equal to 1. So what we're going to do is for or set this M to be some tuple, M1 all the way to Mn, and the sum over these guys are equal to some M, and these are integers. And we're going to define a wave function with entries in this way. And this wave function will be defined as follows. This is exactly our correlator from before, but there will be now actions of these guys. So we will have now a product from 1 to n, and we will have the trace of 1 over ZA minus phi, now to the power MA, acting on these operators A, ZA, in this matrix models with M, comma, X, in this way. So this is basically the correlator from before, only with these insertions, and these act on as lowering operators, if you want, on the highest weight representation, and this guy will then satisfy the following equation. So this psi del ZA of this vector psi will satisfy actually the equation B not equal to A omega AB over ZA minus ZB psi. And these, this omega here, so this is A here. Omega AP is just 1/2 HA HB plus EA FB plus FA EP, and H, E, and F are SL2C generators. So this will act as a matrix, of course, on these M. So for example, E will just, F will just lower one of these M's, goes MA goes to MA minus 1, E will raise it, and H will have a particular eigenvalue. So what one finds is that these operators here, Ka, are actually spin Ka over 2, spin K half representations of SL2. And these are some lowering operators, and this is a tensor product of such states. And the corresponding wave function or conformal block satisfies this KZ equation. This lambda is just a constant related to this x1 up to some proportionality factor. And so you'll find that these original operators will the corresponding conformal block, they form a tensor product of n spin K half representations of SL2C, and they satisfy this KZ equation. But now this KZ equation is a little bit different from the original one, because there is a, this guy here gives rise actually to an irregular singularity at infinity. So you will have an irregular singularity, and it can be, of course, extended to higher degree. I'm just looking at degree 1. So this will have a degree 1 singularity at infinity. And this comes due to the presence of this irregular operator, which we had over there. So this is now the matrix model expression. But yeah, you can see that you could have arrived at this expression by acting with the corresponding currents on the field, and then compute, arrive at the same kind of matrix integral. And finally, you will satisfy this KZ equation. Okay, so yeah, I don't know. How about the time? Still 2 minutes? I see. But I'm well, let's keep it for questions, because I think it was yeah, it was enough so far. So yeah, that's it so far.
Questions?
Yes, thank you for nice talk. So usually the path integral formulation of Liouville has some divergence problem, especially when the central charge is 0 or 13 or something. And that's why the statistical description is very useful. People have used it to derive something like the OCC and correlation functions. And yeah, I wonder if now you inserted this irregular operator, so does this cure any of these divergences, or still need some treatment?
Well, they will actually, I mean, these wave functions here, or the original conformal blocks, they will be some sort of confluent hypergeometric functions. So in that sense, they will behave similarly, but you will have, of course, still, yeah, you do introduce certain divergences, of course, due to the irregular operator, but I'm not sure which divergences you are actually referring to.
Just the vacuum partition function.
Oh, okay, in that sense. Well, in the simplest cases, you can actually get from this stuff a Bessel function, say. So this wave function will be behaving as good or bad as a Bessel function. This would be the case for just 2 of these operators O and 1 irregular operator. But other cases are much more complicated. We just have some integral representations, or yeah.
So is there something like the OCC for the irregular recursion?
But if you want to take 3 irregular operators, or you want to compute OPEs between them, and 3-point functions between irregular operators, this kind of stuff, you mean? That we haven't done. We just look at one irregular operator at infinity. You could take now two other regular operators. DOZZ, I don't know for this
No,
case.
sorry. My question is in this irregular background, right? So I can still reproduce
A 3-point function in that sense.
Yeah.
Yeah, no, that could be, but what we have looked at so far is only the case where these k's are integers, right? So the DOZZ stuff is for very general complex Liouville momenta. These are all integers, so this gives you SL2 highest weight representations. The others are more complicated. So that could still happen because then you will have, here you have finitely many conformal blocks. In those cases, you will have infinitely many conformal blocks. So in that sense, those issues still remain. I mean, potentially it might be behaving a little bit differently, but we didn't look into those.
Time for maybe one more quick question if there are. If not, let's thank Babak for a wonderful talk.